In the first session of our program, we discussed about the problems in the medical area, especially the patient environment and the fire or shock and the related problems. So today we will go one step ahead and especially find out one or two of the issues which is faced by the industry, especially in fire. First, we should understand that electrical installation in hospital is a special thing. There are normal location and medical location. Medical location means a location in a hospital which is classified as Group 0, Group 1 and Group 2, especially Group 1 and Group 2 medical location where biomedical equipment are constantly in touch with the patient and most often the biomedical equipment are bypassing the skin. If we look at the statistics, almost 33 fire accidents happened, major reported hospital fires happened from 2010 to 2019, and about another 24 accidents happened, major ones happened during the COVID time, and approximately 78% of fire due to electrical problems are mainly from places where air conditioner fire is one of the major threat, especially if you have this window or the split air conditioners, and more than 100 or 124 people passed away during this time, especially in hospitals alone. So we actually made a kind of a survey to find out how system can be improved. Then, based on the survey, we categorized the hospitals into three categories. Small hospitals, where we have considered only the inpatient hospitals with inpatient facility. There are small hospitals up to 50 kilowatts of load. There can be one low voltage supply from the utility company, and major loads are air conditioners, fans, small biomedical equipment. And the next level is probably the medium-sized hospitals where the connected load is 50 to something about 300 kilowatt, 300, 400 kilowatt. Here the problem is, instead of going for a high voltage supply, most often each building or each part of the building or some part of the building, there are multiple LT supplies from utility, multiple low voltage, low tension supplies are taken. Then once when multiple supplies are taken, sometime the wiring practices are not followed properly. These hospitals, the kind of load, majority is air conditioners, then X-ray machine, CT scan, light fittings and fan, small biomedical equipment, and so on. Then we have the large category of hospitals where HT supply, high voltage supply is available, proper transformers and all. We tried to make a survey, and the report of the survey, for example, in small hospitals, general subject, for example, whether they have a responsible person or whether people know where the electrical switchboard or where the MCB distribution board are there. If we ask the hospital people, yes, they know where the switches sockets are there, but most of them doesn't know where the MCB DB is placed. That means in case of any disconnection, then it's a little bit trouble. Technicians, most often there is no tools available, and most often they don't know the circuits from where the DB, through which direction the routing of the cable is carried out. There is a socket. If we ask which MCB is connected to this DB, then probably most of the time, 70% of the cases, this information is missing. Most often, small hospitals, in case of any doubt, they call their contractor, who is probably who did the job a few years back, to understand or to know further. With respect to safety, in smaller hospitals, smaller to medium, most of the safety requirements are unknown. It's very rarely known. The installation looks like a TT, but most often the system earthing, which is the most important for electrical safety. It looks like TT, but it's a very, very inefficient way of, let's say, TNS or TNCS. And subjects like fault loop impedance are rarely known. RCDs and earth fault protection in hospitals which is more than 10 years old. Most of the hospitals RCDs are there are no RCD. And hospitals which is less than 10 years old, of course, in some of the cases, RCDs are used. Probably 10%, 20% of the circuits have RCDs. Safety services installed. Safety services means for the firefighting or emergency, the systems are installed, but it is not maintained well. Most often, it's not in working condition. Fire survival installation is very rare. This is the first part, the safety subjects which I have shown is for the general electrical installation, whereas for the medical location, let's say group 1, group 2 medical location or group 2 medical location where continuity of supply is necessary. In most cases, this subject is mostly unknown, unfortunately. Class 2 medical location shock reduction measures or group 2 medical location, the shock reduction measures are very, very rarely known. One of the subject here is supplementary equipotential bonding. I explain it later. And the subject like EMI, EMC is very much unknown. In most of the hospitals, not most, almost 100% of the hospitals, the management is very much interested to improve the system. But most often, the guidance provided by the expert is not correct. I would say most often they are misguided. In large hospitals, the information about general, for example, there are responsible people available, technicians available, sometimes engineers are available. But again, very rarely electrical engineers are there, but most often there is somebody who can take care, and they are trained people. Approximately 50% are known and they know what to do, and they are trained. Again, in most of the cases, in case of doubt, they have the habit of calling the electrical contractor to find out what exactly has happened or what exactly has done. In these cases, overload protective devices are installed. Protective devices such as from the starting, for example, air circuit breaker, molded case, MCCB, MCB, fuses, all those things are installed. So chance of fire due to overload is mostly less in this particular case because proper devices are there. Unfortunately, the devices are not tested. So we really don't know whether these devices will trip or not. You must have seen the first days our video where there was a fire in an appliance. The fire has become a major fire. The ignition has become a major fire because the protective device didn't trip. We generally call fire due to overload or short circuit. Actually, the problem is the fire is because of non-disconnection or delayed disconnection of the protective device. With respect to information on safety in large hospitals, the system earthing like TNS, TTIT, system earth is very rarely known and most often it is misinterpreted. Again, the system looks like a TT, but here in a larger hospital, this situation is even serious than a small or a medium hospital. In a small, medium hospital, of course, the supply is LT, whereas in a larger hospital, the system looks like TT because, but unfortunately, very, very inefficient TNS or a TNCS kind of thing. Fault loop impedance and disconnection, unknown more than 90% cases. RCDs and earth fault protection, very rarely used in modern hospitals. Yes, of course, nowadays the number of usages are increasing. Safety services are installed and they are maintained well, almost in 50% cases. Then fire survival installation for safety. So most often, the fire survival people think that fire safety is about using a wire which can withstand a fire. It is not like that. Fire survival installation means the whole electrical installation shall withstand for certain time. It is not only the wire. So you should also think you have to change a little bit. It is not only about wire, the whole electrical installation should they have to survive fire. Safety in medical location, continuity of IT supply, mostly it's unknown 80%, and about 20% it is known. Class 2 medical location shock reduction measures are again unknown. 90% cases, the shock reduction supplementary protective equipotential bonding is missing. In some hospitals, of course, there is a rubber flooring made, thinking that this may protect from shock, but that most often in a conductive location where conductive fluids are sometime on the floor, it will be very difficult to achieve safety in that way. Of course, that the rubber or the plastic flooring is required, but protective equipotential bonding is also required. You cannot avoid it. Then EMI, EMC is most often is unknown, but almost all of them are aware of the shielding in the radiation application in certain areas. They know that EMC protections are necessary, because without that, the equipment will be quite dangerous. The managements are very much interested in safety measures. Again, I would say misguided. One of the misguiding, I always make a comment about this. People think that by making thermography, the complete electrical safety is made or possible. Actually, this is wrong. Thermography, it can, of course, tell you the hotspots. It can increase the safety, but it doesn't mean that complete safety is achieved by doing only thermography. You have to make all the recommended safety measures as per IS 732. There are 18 inspection points and 10 testing points plus medical location additional testing. Over and above, you can do thermography. If you do only thermography, please don't think that we will achieve safety. Here, the problem of thermography, the live conductors are, the loose contacts in the live conductors are known, whereas the earth conductor or protective conductor, you cannot find out the loose contacts and problems in the protective conductor. So the IS 732, also the National Electrical Code 2023, which is launched 6th of January, has recommended 2 testings which can find out loose contacts in a wiring. Test number 1. This is called as continuity resistance of the wiring. You are supposed to measure the continuity resistances. And test number 2 is fault loop impedance. With these 2 tests, loose contacts not only in the phase or neutral conductor, but on the earth conductor also can be found out. So another misguided system is sometime, I would say, fire survival cable can reduce fire. Because, for example, in one of the report, I have seen that there was an air conditioner fire, and the report says all wires should be fire survivable. Actually, this is again not the correct information. The fire has started from the air conditioner. Even if you use a fire survivable wire, the problem is in the air conditioner, not in the wire. So the recommendations in the standard, if we look, you should use class 2 copper conductor. Fire resistant installation for safety services are mandatory. The wiring system shall be mounted and installed in such a way that circuit integrity will not impaired during fire, and so on. Another issue is EMI. I would say harmonics is one of the subject in EMI, especially in the hospital. There are several issues: harmonics and interharmonics, signals superimposed on power lines, voltage fluctuation, voltage dips, voltage unbalances, power frequency variations, induced voltages, and so on. There are several issues because in a hospital, a lot of equipment are used. This particular video, you can see. So this is, in this particular case, you can see on the screen the white grains. These white grains are actually because of an EMI issue. And this EMI, most often it is from, for example, an LED light which is close by. or maybe from an air conditioner nearby, inverter air conditioner, or maybe from an UPS nearby or on the next room. So what happens is, because of this kind of misreadings, I put the video again, you can see the grains here, the white grains. Because of this misreading, imagine a patient is connected with biomedical equipment, and the equipment are showing some wrong readings. It can lead to a serious incident. So this is actually very, very important. EMI is a very important subject in hospital. The second issue which we face is fire from air conditioner. You can find out a lot of news from the our newspaper and media about the fire in hospitals. One classic example here, there is a fire from the air conditioner indoor unit. Now, for your information, the government of India has made ISI marking mandatory for air conditioners from 1st of January 2023. So ISI marked air conditioners are only can be sold in the market from 1st of January 2023. And here there is a small issue in the sense, the test standards which the air conditioner compliance required is IS 1319 2017 and the IS 1319 part 1 and 2 for unitary air conditioners and split air conditioners. So in the market, whatever you are buying nowadays, you have to check whether the air conditioner is ISI marked. But I would recommend not only that, there are some additional standards with respect to safety. For example, IS 302 part 1, this is talking about safety of household and similar electrical appliances. This is 302 is actually a mandatory requirement for all electrical appliance which is used. And this 302, again, it is from IEC 60335. Part 240, there is an IS code or IS standard 2018. This standard is specifically requiring additional safety measures for air conditioners. The issue is mandatory marking. The recommended standard is only 1319, but in the letter, mandatory marking for 302 and 60335 240 is not mentioned. As a result, there is a chance that manufacturer may not test as per the 302 or 60335 240. So once when you buy an air conditioner, you must check whether it is ISI marked. Plus, you also please check whether the air conditioner is tested for all the safety parameters as per IS 302 and 60335. For example, I just made a comparison. We made a detailed study and one report we are trying to publish. For example, point number 3, high voltage test, electric strength test, which is very, very important for an electrical appliance because most often failures are due to insulation failure. The IS 1319 is asking for 1,000-volt test for 2 seconds. That means between the phase or the neutral conductor and the body, 1,000-volt is applied for 2 seconds and the equipment shall not fail. But in reality, the duration which is shown 2 seconds is quite less. In practical, they are supposed to make the test for 1 minute. The IS 302 recommend to make this test for 1 minute. So the ISI marked air conditioner, you can be sure that 1,000-volt 2-second test is made, but you should also check IS 302 whether the air conditioner is tested so that a higher, the test is made with respect to continuous voltage 1 minute. Say, for example, transient over voltage. Every electrical appliance which is used in an electricity, we are supposed to, or the equipment manufacturer is supposed to categorize the equipment as per over voltage category. Air conditioners are actually part of fixed electrical installation. They are not portable appliance. They are fixed electrical installation. Generally, they have to come under over voltage category 3. That means the air conditioner must be tested with an impulse voltage of 4 kV. So an air conditioner tested as per IS 302 coming under impulse voltage category 3 is the best solution. Similarly, for example, the IS 1319 is not talking about glow wire test, whereas IS 302 talks about glow wire test. So you must be careful while buying new air conditioners. Please be careful. 70% of the fire in hospitals are from air conditioners, especially these window or split air conditioners. So ensure that the new air conditioners which you are buying is having ISI mark and in additional tested as per IS 302. All the electrical parameters are tested. And when you install it, be very careful about voltage stabilizer. If you use a voltage stabilizer, instantaneous tripping of MCBs may not happen. During a short circuit, the MCBs may not trip instantaneously. Of course, overload protection is possible, but the instantaneous tripping may not be possible because voltage stabilizers are adding impedance in the circuit. As a result, fault of negligible impedance or short circuit current is reduced and the disconnection time will be higher, resulting in a fire. You have to be very careful. Now, from the survey, the general findings which we see is a lot of cases there is no protective conductor, there is no earth wire in the final circuit. In the final circuit, in the sense, in the medical location, there are the sockets available. There is no earth wire on the socket. Most often these are disconnected, damaged protective conductor. Number 3 is undersized protective conductor. That means the phase and neutral is 16 square mm, but the earth wire is only 2.5 square mm. This is actually a violation. Up to 16 square millimeters. Phase, neutral, and earth must be same size. The RCDs are not there. Large hospital with own transformer has non-standard system earthing. TT is widely used instead of TNS as recommended on regulation standards and so on. Continuity test to find out loose contacts not carried out, unfortunately 100%. Fault loop impedance not carried out 100%. Methods to reduce insulation degradation not carried out. Too much earth pit, violation of safety requirement. Isolators are used instead of MCBs. Origin of a circuit is not traceable. These are some of the issues which we see, which we find. Now, please note that in a properly designed, erected, and tested electrical installation, overload and short circuit shall not create any incident because these protective devices are supposed to disconnect, provided they are not only selected properly, installed properly, but they are also tested properly. Most often, this testing, especially fault testing, the disconnection of the protective device during an earth fault is very, very rarely happening because we use a kind of a TT system. TT system in the sense the transformer neutral is connected to two earth pit and the panel board earth bus bar is connected to a separate earth pit. As a result, it becomes a TT system, but sometimes underground these are also connected. Then it becomes an inefficient TNCS system, which is very dangerous. Disconnection recommended within the recommended time of 200 milliseconds may not happen. You must understand that wiring and the equipment can withstand fire or withstand a higher current only for a short time. So basically, the disconnection may not happen. Now, with respect to fire, there are a few concepts which is included in the design standards. One of the concept which is included is, for example, in the table, in the figure which you are seeing, the green color, power in watts. It is nothing but the power dissipated due to a fault. Whatever the maximum size of the power, let us say, for example, 4,000 watts or 2,000 watts, If the fault is cleared within 3 seconds, so here 1, 2, 3, 3 seconds. If the fault is cleared within 3 seconds, the chance of ignition of fire is quite less. Or if the heat dissipated is less than 15 watts, even for a longer duration, then the chance of heat or chance of ignition of fire from electricity is quite less. But limiting the heat dissipated to less than 15 watts is quite difficult. We have to have a power supply with a limited current, which is another technique. But the simplest technique which we can implement is ensure that the device is able to disconnect within certain time, within the recommended time. Similarly, the second concept is a heat dissipation due to a fault. If it is limited within 5 seconds, then the chance of ignition is possible only under some conditions. Similarly, if the heat dissipation is limited to less than 100 watts, ignition is possible only under some condition. If exceeding these limits, of course, electricity is dangerous. It creates fire, and the electrical power source is classified with this particular idea: power source 1, 2, 3, and electrical wiring designs or electrical wiring recommendations in the standard are made based on these power source classification as well. When we select an MCB for a typical application, please be sure that it is not just like for a typical application thing that today I need 10 amps current and tomorrow I may increase it to 60. So now itself, let me use 63 amps MCB. This is a wrong idea. So the correct way of using protective devices, first of all, the protective device is to protect the circuit. So in order to protect the circuit, the first item which is on the circuit is the wire. So the device should be selected based on the wire size. And here you must understand that every protective device have got a conventional disconnection time and conventional disconnection current. Conventional disconnection time is 1 hour, up to 1 hour. Conventional disconnection current is 1.45 times. Similarly, positioning of the device, very important. For example, I just put the tripping curves of MCB, B, C, D, MCB. All the three types, B, C, or D, up to 1.13 times the nominal discharge current, the device is not supposed to trip, no tripping. Similarly, 1.45 times into IN, the disconnection time, this is called as conventional disconnection current. Conventional disconnection time is up to 1 hour for devices less than or equal to 63 amps, 2 hours for devices more than 63 amperes. It means your wire should be able to withstand a current of more than 1.45 times the rated current of the protective device for at least 1 hour or 2 hours in case of device more than 63 amps. Similarly, 2.55 times the rated current, the devices will trip within 1 second, and the instantaneous tripping is happening 5 times IN, 10 times IN, 20 times IN for BCD type MCBs, as shown the disconnection time. So if you use stabilizer, the problem is here the instantaneous tripping, or sometime 2.55 times the nominal current. These calculations are missing. As a result, the MCBs may take much more time to trip, ending up with a fire or an accident. With recommend to the requirements of the standards and codes, all of you know very well that we have the National Electrical Code of India 2023. With respect to hospital, the NEC has got 8 parts. Part 1 consists of 22 sections. All these 22 sections are mandatory. Part 2 talks about supply system like DGs and transformers. Then part 3 talks about special electrical installations such as bathrooms and wet areas. And for example, part 3, section 9 talks about medical location, group 1 and group 2 medical location. Please download the standard which is available at free of cost. You have to go to the BIS sales portal and you can download the standard at free of cost. It's a 800 plus page document. Now we are starting mass awareness campaign for the National Electrical Code. Probably we will be able to support you in understanding the standard. The standard NEC recommends 19 inspection points in section 1 part 1 section 17, and there are 10 testings included in the NEC. These 10 tests we have explained last time. Also, we are explaining in several programs. It starts with continuity of conductors, then insulation resistance of low voltage and extra low voltage, insulation resistance or impedance of floors and walls is one of the test. It is just to find out whether the floor or the wall is in a dangerous situation to create a shock. Then the test number 6, automatic disconnection of supply. Please note that out of these 10 tests, 4 tests you doesn't require power supply. Power supply should be in off condition. And 6th test, power supply should be in on condition. On condition in the sense you need the actual power supply. Here, sometimes we face a challenge. Once when we go for the client, before commissioning the transformer, they say, you come and do a test because now we have a temporary power supply, and with the temporary power supply, we are forced to do the test. Actually, this is not correct. If we do the test with a temporary power supply, with the actual power supply or actual transformer, we really don't know what is going to happen. So we need to do the test, the 6 tests with the actual power supply, actual transformer, actual DG. Medical locations are very special. In the last presentation, part 1 of our program, we explained Amaya explained it very clearly and in a very understanding way. So these locations, there are several special requirements. We also explained about micro shock, macro shock, and the problems with respect to micro and macro shock. Also, the additional safety measures required in a hospital in comparison to a normal electrical installation. These are actually the points which I am going to explain. These are actually included in the National Electrical Code as well as the regulations. So these becomes mandatory. Power distribution and safety. First of all, the system earthing must be at TNS for general areas, and automatic disconnection in general areas is a safety measure. Continuity of supply in group 2 locations as per IS 17512. Of course, these the NEC National Electrical Code also explains both these requirements. Patient environment. Then in general care areas, 500 millivolt under normal condition. The potential difference between 2 simultaneously accessible metallic parts must be lesser than 500 millivolt in general care areas, and in critical care areas, the voltage between 2 simultaneously accessible parts should be lesser than 40 millivolt under normal condition. This 540 is under normal condition. So the supplementary equipotential bonding must be very, very efficient to reduce the potential difference lesser than these. You see, 40 millivolt is a negligible voltage, but this more than 40 millivolt itself sometimes is deadly for a patient. And during fault condition, the potential difference must be limited to less than 25 volt. So very important supplementary protective equipotential bonding. The next part is current loop. Potential differences and unintentional current flow through patient. So this is actually a serious issue in a hospital. Here, what you should do is all intensive care units must have single earth for each patient, isolated from safety earth. So this is actually a system which is recommended for hospital. It doesn't mean that you need to have separate earth pit. The recommendation here is each single patient or an area where you have an ICU, each patient area should have only one earth. That means a very good equipotential bonding must be made, and this can be isolated from safety earth. This is a kind of a functional earth. We will discuss it maybe in another program, because this is itself is a much bigger subject. Maximum 40 millivolt potential difference in any conductive surfaces must be made. So then you can also go for safety measures such as electrical isolation with an isolation transformer, barriers, then increased safety measures are also required. Similarly, the NEC is recommending additional testing for hospital medical environment. There are 5 tests. The first one is insulation monitoring device should be tested. The second and third are both related to shock reduction, supplementary equipotential bonding, and facilities for equipotential bonding, the efficiency of these bondings. Please note that bonding means you take a wire and connect it to metal parts. Then you check and find out the actual potential difference between these two parts, and it should be lesser than 40 millivolt, for example. Then safety services, and the standard also recommended here the frequency of these checkings as per the standard. Similarly, the NEC had given one more information. Sorry, there is a spelling mistake. It is NEC of India, not NEF of India. The buildings are classified based on the National Building Code, Group A, Group B, Group C, Group D, Group E installations. Now, Group C, the medical and hospital and sanatoria comes under Group C, especially C1. Here, the recommended periodic verification for the general area is 2 years. So please make a note of it. Now, with respect to the concept, most of you know very well, because I am showing or explaining about this safety measure in almost every electrical safety class. The concept of safety, there are 2 concepts. The first one is called as the earthed power supply, which is for general locations where protective equipotential bonding and disconnection of the supply is mandatory. Whereas the concept number 2 is for medical location or for safety services, where unearthed supply can be used. In an unearthed supply, the power supply continuity is ensured even during the first fault. So we have to, or the person who is using, or the person who is designing or making a safety audit, he must understand the difference between these 2 systems, and he should make it. When it comes to earthing, one more point you should understand is electrical appliances are of 3 types. In fact, there are 4 types. Class 0 is also there, but nowadays class 0 is banned. So basically, electrical appliances are classified into class 1, class 2, and class 3 appliance. Class 1 device require protective earthing. Class 2 devices are basically device with 2-pin plug. Protective earthing is not necessary, but sometimes functional earthing is required. Here on the right side, the symbol shows functional earthing. Class 3 devices are operating with a very low voltage, sometimes a voltage which cannot create a shock hazard. In this case, also protective earthing is not required, but functional earthing may be required. So whenever you make a protective equipotential bonding, first you should also consider the type of equipment which you are going to use. And the functional earthing, the recommended color is cream. So understanding the earthing requirement in a medical area, it is a little bit critical. It is a little bit technical as well. But you know what I am showing in the picture, 5017, 1819, and 20. These are called as the earthing symbols, which is mentioned in the appliance. The appliance manufacturer should take care of his requirement, and appropriate marking must be made. The installer or the designer of that particular location, he has to understand the meaning and the method of making the earthing, and he should make. As I said, in the National Electrical Code, you can see this particular picture. This particular picture is explaining about protective equipotential bonding. Protective equipotential bonding means all dead metal parts in your building, such as M stands for exposed conductive part, CP, these are some kind of metal installations, extraneous conductive parts. If you go for a TT system, then one building require one earth connection to earth pit. MET must be connected to earth pit at least once. Then if you go for a TN system, the MET has to be connected to the transformer neutral, and this is called as protective equipotential bonding. What is required extra in a medical location is number 4, which is called as supplementary equipotential bonding. So this picture is also included in the NEC, and near to that, a lot of explanations are given. Please go through it and make it. So earthing is called as protective earthing, protective equipotential bonding, which consists of main and supplementary equipotential bonding, and automatic disconnection of supply within the specified time. If this safety measure is properly implemented in a hospital, the chance of fire from whatever reasons, especially air conditioner or fire from the medical locations, it can be almost nullified. This picture from IS 3043, again, just to show that earthing doesn't mean neutral two separate pit, bodies two separate pit for DG and the transformer. It is absolutely wrong. What you should do is a protective equipotential bonding. Neutral of the transformer or DG has to be connected to an earthing bar. I am talking, this picture is basically for place where you have your own DG, body, alternator, and neutral connected to the common bus bar. And this is the correct way. Now here in IS 3043, you can see this particular symbol, which is called as 5020. It is not exactly to an earth pit. It is the chassis earth. Chassis earth means the frame or the chassis where you are going to. It is the chassis earth is also nowadays called as functional bonding. Similarly, the MET has to be connected to extraneous conductive parts, and this is the correct way of earthing. You can also find the additional pictures in both IS 3043 and IS 732, and the explanations are also provided. Another important subject is fault loop impedance. Engineers, those who are practicing in the hospitals, please note that the equipotential bonding and fault loop impedance both are highly important. Both are included with very good explanations in the National Electrical Code. You can also find the tables, fault loop impedance recommended for each type of MCB. So the simple method which you should understand is resistance of the wire influence the disconnection time. Testing of fault loop impedance is highly important. Now I am moving the cursor in the location, live metallic body. It is connected to the neutral of the transformer through a metallic connection, metallic conductor. So the exposed conductive part or the extraneous conductive parts are finally connected to the neutral of the transformer through a metallic connection, and this metallic protective conductor must run along with the phase and the neutral conductor. Don't try to route it through a different route. So there are some rules which has to be followed here. Please don't believe the subjects such as chemical earth, analog earth, digital earth. There are a lot of claims happening in the market. People claim that I have a digital earth which will solve all your electricity related problems. Don't make earth farm all around your hospital because this is also not correct. These things will create more problem. Average, if we look all around the hospital, a lot of hospitals have got the earth farm 50 to 100 numbers, which is not correct. The correct way of earthing, I just skip these slides. I actually don't want to show that, but unfortunately I forget to hide it. So the correct way of earthing is protective equipotential bonding. So lightning protection, functional earthing, protective earthing, everything must be interconnected. Now, one important subject which I would like to explain, because during the last program, a lot of people asked about lightning protection. Somebody said there is some court order or there is some ruling and so on. I would like to explain that particular subject here. In India, there is a nice story about lightning protection goes on. Manufacturers claim that I have an advanced lightning protection rod, which is very special, and it can protect up to 100 meters or sometime even much more than 100 meters. There were some videos where people are claiming up to 2 kilometers. One rod protecting 2 kilometers of radius is really a nice idea, but not practical. So basically, these non-standard system claim that it protect up to 100-meter radius, and you need to have one down conductor, 70 square millimeters of copper wire, and one earth pit. So basically, one rod, one down conductor, and one earth pit. And this down conductor can be routed through anywhere, most often through electrical shaft. And then the owner of the building believe that he is protecting not only his building, but he is also protecting all his neighbors. This is absolutely the only word to be called is it's a non-standard system. National Building Code 2016 recommended not to use this system. It cannot provide any safety, and routing down conductors through shaft is a serious violation of safety. Now, these manufacturers, as an argument, these suppliers, they claim that this is as per the French code. It is as per the French standard. Then users sometimes believe that French standard is also a good standard. Let us follow. But please note that the French standard is asking not for one down conductor, one earth electrode. The French standard is explaining the system in detail. You need to have several safety measures in a building. Over and above, you see this item number 1. This is the ESE rod. So basically, you need to have serial number 1 to 18. If you go as per the Indian standard ISIC 62305, you can achieve safety by using items serial number 2 to 18. Item number 1 is absolutely not required. Whereas the French code is asking to put an additional rod. Please note, additional rod. Whereas the same system, manufacturers take it to India and they say that one rod protect 100 meters. You take one wire and connect to the earth pit, your lightning current will go, like water through a pipe, which is absolutely wrong. So one rod, one down conductor, and one earth pit is a marketing tool, and this marketing tool is actually fooling engineers. All engineers are made fools, because if we know how a high frequency current works, then you will not accept this one down conductor principle. Also, there was a big fight went on in the market regarding this non-standard lightning protection. In a meeting in BIS, there was a delegation from France and from Australia came. There was a meeting held. Those documents are available in the public domain. So one French manufacturer agreed that ESCs are not installed as per the national French code. So they told that yes, there is a French code and you are supposed to use it as per the French code. But in India, nobody uses ESC as per the French code, and they also blamed that the consultants don't know about the French code. As a result, the consultants are responsible for the one rod, one down conductor, one earth electrode. Consultants or the safety auditors are responsible, and the manufacturer is not responsible. Basically, they made the story of one rod, one down conductor, and one earthing, sold it, and finally they say, I'm not responsible. If you still wanted to use these non-standard items, please download the National French Code 17102, then do as per this particular code. Don't believe the manufacturer's claim of one rod, one down conductor, and one earth pit, because it is just to fool engineers and to make business. Lightning protection must be carried out as per IS IEC 62305. Especially in hospitals, you must follow this particular standard, because the electromagnetics of the lightning can damage your electronic equipment. Now, a properly or a well designed and installed lightning protection only can protect your electronic appliance. So with this, I would like to stop today's presentation. And as I said, 99% of the electrical accidents are we are able to solve. We can avoid, or these accidents are avoidable. Please note that the installation must be designed, erected, and tested as per the National Electrical Code of India 2023. So if the building is made as per this particular code, you can be sure that 99% fire accidents can be avoided. Then number two, as Mr. Dominic told, 26th of this month, the coming week, we are going to launch, or we are going to start the activities of National Federation of Engineers for Electrical Safety. Now, with the NFE, we are trying to make a large scale classes on NEC. Classes in the sense, 1 hour or 2 hour class may not be sufficient to learn the whole subject. It may be sometime 30 to 40 hours of training. So we are going to start long-term trainings. We request you to participate in the programs so that you also will be able to learn a lot. So by this, I would like to thank all the participants. We go for the question answers. Over to you, Ms. Lakshmi.